In the name of Almighty Allah, the most gracious, the most merciful. As Muhammad, peace be upon him, narrated, if anyone travels on a road in search of knowledge, Almighty Allah will cause him to travel on one of the roads of paradise. Hello everyone, this is Dr. Tariq Masood. Thank you very much for watching my videos and your exceptional support to make this channel a grand success. We are a partner. Please subscribe and share our channel if you haven't done so far. We as a team can work together to convert challenges into opportunities and opportunities into success stories. These success stories can be monetized into value addition. Thank you very much for your precious time. Okay, today I'm going to discuss my lecture number 8 on Smart Grid Control Challenges Model. Before my lecture, I used to read a Quranic verse. Qala Rabbi Shrahli Sadri wa Yassirli Amri Wahlul Uqdatam min Lisani Yaqfa Qawli Allahumma Rabbi Zidni Ilma. Okay, this is my acknowledgement page. I pay my deep gratitude to all professors from bottom of my heart for their unprecedented support during my student era. Professor Dr. R.K. Agarwal, former Director of Center of Sustainable Power Distribution, University of Bath, UK. He was my supervisor and we worked together more than 12 years. Professor Dr. Abdulati Adris, late former APRI Technology Managers, California, USA. Unfortunately, Professor Dr. Abdulati Adris passed away in 2016. Almighty Allah bless him, highest place in Jannah. He was my mentor and external supervisor. Professor Dr. Muhammad Afzal Haq, former VC NED UET Karachi. Professor Dr. Nad Mohan at University of Minnesota. Professor Dr. Ataullah Shah, VC, Crocram International University, Gilgit. Professor Dr. Flor from Romania, Professor Dr. Mohammed Jamal, Professor Dr. B.S. Chaudhary, Dean MUET Jamshoroo, Professor Dr. Nasir Al-Umadi, former Dean Qatar University, Professor Dr. Akhtar Kalam, Head of Smart Technology from Victoria University, Australia, Professor Dr. Suhail Aftab Qureshi, former Dean UET Lahore, Pakistan, Professor Dr. D.P. Kotari, former VC IIT India, Professor Dr. Rana Abdul Jabbar, CEO ADP Pakistan. He was also Principal of RCT Gujranwala. Okay, Smart Grid Operation and Control Challenges Model. Before starting a key takeaway points of my lecture number 8, just want to give a recap or highlights what we have discussed so far up to lecture number 7. In lecture number 1, we have discussed electricity required for our civilization, electric power functionality, energy efficiency from generation to consumptions, ultimate goal for smart grid. We have also discussed in our lecture number 2 power system infrastructure development, power system complexity, power system limitations, reactive power significance and management, reactive power management challenges to manage reactive power, balance reactive power, challenge at AC power system. We have discussed lecture number 3. Number 4, we have discussed dealing with thermal limit, increasing a transmission conductor current carrying capacity, DTCR, dynamic thermal circuit rating technology. We have also discussed first generation compensators, second generation compensator, and third generation reactive power compensators. Okay. We have discussed lecture number 6, impact of dynamic voltage support, fault induced delayed voltage recovery phenomena, FIDVR, STATCOM, ensuring voltage recovery, subsynchronous resonance, SSR phenomena. In number 7, we have discussed TCSC, structure and functionality, TCS, operational characteristics, fundamental of voltage source converters. Okay, today we are going to discuss lecture number 8. So before lecture number 8, on my next slide, I'm going to give us my lecture plan, 100 lecture program, and then I will give you key takeaway points of lecture number 8. This is my 100 lecture plan, 8 to 9 months. We will discuss fax technology concept, power semiconductor devices. We will discuss voltage source converters, self and line commutated current source converter, SVC STATCOM operations, static series compensators, static voltage and phase angle regulators, combined compensator UPFC, special purpose fax devices, last not least application of fax devices. We will discuss a few models already implemented in the United States of America. So what is ultimate goal of fax technology concept? Shaping the global energy or resolving a gridlock, delivering a clean and poor power in the network. That would be the ultimate goal of the smart grid or by implementing fax technology. Okay, fundamental voltage source converters we will discuss today. We will discuss 3-level quasi-harmonic neutralized 48 pulse VSC functionality in electric grid. So today we are going to discuss. This page is dedicated to all faculty members and students, particularly leadership, department chairs, deans and VCs, the universities as leaders whom I am been visiting since long. Okay, controlling power transfer parameters, fundamental structure voltage source converter. Okay, what it basically demonstrates here. It has a 3 section. First is the DC capacitors, second switching converters, then coupling a transformer, and then sinusoidal output voltage. Function of voltage source converter. The internal topology of converter valves is represented as a box with the valve symbol here. One turn-off device with one parallel diode. Okay. So on the DC side, voltage is a unipolar and supported by capacitor. Okay, this capacitor is large enough to at least handle a sustain a charge discharge current that accompanies the switching sequence of the converter valves and shift in phase angle of the switching valve without significant change in the DC voltage. The DC capacitor voltage will be assumed a constant. Okay, so that the DC current can flow in either directions and that it can exchange DC power with connected DC system in other directions. The AC side is generated AC voltage connected to the AC system, as we have seen demonstrated here. Okay, the AC voltage source with low internal impedance, a series inductive interface with the AC system, usually through a series inductor or a transformer, as we coupling transformer as we demonstrated, is essential to ensure that the DC capacitor is not short circuit and discharge rapidly into a capacitive load such as a transmission line. AC filters may be necessary. The series inductive interface to limit the consequent current harmonics entering the system, AC system side. Basically, a voltage source converter generates AC voltage from a DC voltage. Okay, this is the DC voltage, and over here it is generated over here our AC voltage, often referred to as an inverter. It has a capability to transfer power in other directions. With the voltage source converted, the magnitude, the phase angle, and the frequency of the output voltage can be controlled. As we know, since the direct current in the voltage source converter flows in other directions, the converter valves has to be bidirectional, and also since the DC voltage does not reverse, turn-off device need not have a reverse voltage capability. Okay, so now on my next slide we are going to discuss the 3-level 48 pulse modulation mode. Okay, for high power fax controller from the point of view of the AC system, even a 24th pulse converter without AC filter could have voltage harmonic which are higher than the acceptable level. Okay. Now, the second part, in this case, the single high pass filter are tuned to 23rd to 25th harmonic located on the system side of the converter transformer should be adequate. Alternative way is go to 48 pulse operation with 8 6 pulse group with one set of the transformer, the 124 pulse converter. Phase shift is this is interphase a transfer IPTC 7.5 displacement. Okay, so it would be desirable to vary the magnitude of AC output voltage, that is output voltage AC. Okay, AC without having to change the magnitude of the DC voltage here. Okay, the 3-level converter is one concept that can accomplish that to some extent. One phase lag of the 3-level converter as I have shown here. Okay, so this is the first lag, this is the second lag, and this is the third lag. This is the positive, and from here is from the bottom here this is the negative side. Okay, the other two phases as I have demonstrated here would be connected across the same DC bus bar and the clamping diodes connected to the same midpoint and for the DC capacitor. It is seen that each half of the phase lag is split into two series connected wells. Okay, as we have seen here. Okay, the midpoint of the splitter wall is connected by diodes to midpoint as shown on the face of it. This may seem like a doubling the number of wells from 2 to 4 per phase lag in addition to providing 2 extra diodes wells. Okay, now what we have to observe further here. Okay, the significant disadvantage of 3-level converter is that with increasing a conduction angle, amount of third harmonic flows into the midpoint of the DC capacitor. This current generates a third harmonic voltage across the capacitor. In order to keep this harmonic voltage without acceptable limits, to avoid generation of additional harmonic in the AC output and increasing in the converter current rating, the size of DC capacitor has to be increased compared to that of the 2-level converter. What are the additional observations here? So the additional observations here, the output voltage waveform contains fundamental frequency components and harmonics. That is the first here. Second, the output voltage pulses are asymmetrical about the zero crossing of the sine wave because the sawtooth frequency is an odd integer multiply of the main frequency. Even multiply will create asymmetrical about the zero crossing, which will contain even harmonics. Non-integer multiplies are even worse as they create a sub and super synchronous harmonic as well. When the frequency is higher, above few kilohertz, this asymmetry becomes insignificant, but at the PWM frequency, synchronization of control signal is important. Second, with the fixed sawtooth wave, increasing the magnitude of the sine wave will increase the conduction time of the device 1 and decrease the conduction time of device 4. So as we have seen into leg 1 here. Okay, so as the control sine wave peak equal to the peak of the sawtooth wave, the mid notch in the AC output voltage disappear. If the control sine wave is increased to a higher and higher magnitude, more and more notch will disappear and the output voltage will eventually become a significant square wave per half cycle. It is clear that the AC output voltage can be controlled from 0 to maximum. The sine wave itself can be modified with notch to create other effects on the waveform. Okay, on my next slide we will further discuss 3-level quasi-harmonic neutralized 48 pulse modulations. So as we have discussed in our earlier lecture, So just give a brief about gate turn off power switches here, and these are connected here. If we can see here, the conventional thyristor device has only the turn on control. Its turn off depends on the current coming to zero as per the circuit and system condition. In devices such as the GT turn off, GTO, integrated gate bipolar transistor, IGBT, most turn off thyristors, MTO, and integrated gate commutated thyristor, IGCT, and similar devices have turn on and turn off capability. These devices, referred to as a turn off devices, are more expensive and have high losses than the thyristor without turn off capability. However, the turn off devices enable converter concept that can have a significant overall system cost and performance advantages. These advantages in principle result from the converter which are self-commutating as against the line commutating converters. Compared to the self-commutating converter, the line commutated converter must have an AC source connected to the converter. It consumes reactive power and suffers from the occasional commutations failure in the inverter mode of operation. Therefore, unless a converter is required to function in the two lagging current quadrant, only consuming reactive power while converting active power, converter applicable to fixed controllers would be of the self-commutating types. There are two basic categories of self-commutating converters. The first is a current source converter, in which has the direct current always has one polarity, and the power reversal takes place through reversal of the DC voltage polarity. Second is the voltage source converter, in which the DC voltage always has one polarity and power reversal takes place through the reversal of the DC polarity. Okay. Now, after application of GTU, IGBT, MOS, IGCT, MTOs depend on the power rating. So same here, this is my P is equal to V as sending end voltage, receiving end voltage, and my sending end and receiving end angle, and this is my line reactance. Okay. Now I am adjusting VS and VR by implementing a STATCOM. Okay, if you can see the STATCOM, it's showing inductive mode of operation, and then it also showing the capacitive and inductive mode of operation. Both operations it demonstrate. Okay, the converter based voltage regulator is a second device here in order to adjust the voltage. Okay, so this is my second phase here. Okay. To adjust the line reactance, we are using a static synchronous series compensator, that is SSC, to reduce the line reactance or line impedance in order to deliver maximum power. Okay. To improve or to adjust the converter base phase angle, so I am using here the converter base phase angle to adjust my power angle. This is my sending end, generation side, and this is my load side, receiving end. So that is how the 3-level quasi-harmonic neutral 48 Hz modulations are working in order to deliver the required results. Okay, voltage source converter based technology, which is the DC voltage always has one polarity, and the power reversal take place through reversal of the DC current polarity. So on VSC applied functionality, so what we can deliver here, the first here, the STATCOM, we can control the voltage here. Second, SSC, static synchronous series compensator, to adjust the line impedance, control the line impedance. 3 is a unified upper flow controllers, UPFC, voltage, line impedance, and power angle. Number 3, back-to-back STATCOM, voltage and a power transfer control here. And number 3, interline a power exchange, IPFC, used to interline the power exchange. So Thank you very much for your precious time. This was my last slide. On my next slide, we will discuss further on state-of-the-art technology and cost factors. Thank you very much for your precious time. Okay, conclusion. Today we have discussed 3 sections of fundamental of voltage source converters, 3-level quasi-harmonic neutralized force pulse modulations, and voltage source functionality in electric power grids. Thank you very much for your precious time. We are still working on shunt and series controllers functionalities. Okay, these are references, the paper which I have published in different conferences and journals. Thank you very much for your precious time. Together, everyone achieve more. Please don't hesitate. Send me your feedback and comments. t.masood.dr@bath.edu. Please stay at home, safe, inspired and blessed. Thank you very much again for your precious time.